So addition rule, complement rule from 5.2. The last thing we're going to go over in 5.3 is the multiplication rule. We're going to keep this pretty simple too. We're going to make sure that we're using independent events and we're not going to use dependent events. So the first thing we're going to do is define independent. And again, just like the mutually exclusive, disjoint, you're not going to have to know this definition. I'm not going to ask you it outright. All of the ones I give you are going to be independent because then we can use the multiplication rule. So actually we're going to use it more in 6.2, this definition, so maybe you do need to know this definition. But two events are independent if something is in event E, it doesn't affect the probability of event F happening. So if you're looking at something like rolling a die and flipping a coin, those things are going to be independent because when you flip the coin, it doesn't matter what your outcome was when you roll the die. It doesn't matter. It's still going to be 50-50. Something that's dependent would be if you draw a card, look at it, keep it in your hand, and then draw another card, because once you do that, the probabilities are going to be changed for that second card because you no longer have 52 cards anymore, you've got 51. So the probabilities are going to be a little bit different. So that's what it means to be independent and dependent. We're going to focus on the independent ones because that makes the multiplication rule a lot easier. That's basically what we're going to do. Oh, we do. Okay. All right, so it says you draw a card from a standard 52 card deck and then roll a die, and we're looking at drawing a heart from the deck and rolling an even number. It's going to be independent because it doesn't matter if you got a heart or not, because when you roll a die, you still have a 1 out of 6 chance of getting each individual number. And then right here for the second example, if you're drawing 2 cards and you're looking at drawing a heart and drawing a heart, they're going to be dependent because when you draw a heart, the first one, it's going to be your probability of getting a heart is 13 out of 52 because there's 13 hearts out of 52. But now for your second one, there's only 51 cards, so now your denominator is different. It's going to be a 51. So your probability is going to be different for that second one. And then for your numerator, it's going to matter if your first card was a heart or not. So if it was a heart, your numerator is down to 12 because you've got 12 hearts left. But if it wasn't a heart, then you've still got 13 hearts left in the deck, and your denominator is going to, or sorry, your numerator is going to be a 13. So that's just kind of showing what independence is. Okay, so as long as they are independent events, you've got this formula right here. If it's and, the probability of E happening and F happening, so probability that we roll a 2 and get a heads when we flip a coin, probability of both of those things happening, the probability is just going to be, this and is going to change into a multiplication right here. So or turns into addition, and turns into multiplication. So for this one, it says, probability that a randomly selected female aged 60 years old will survive the year is 99.186%. What is the probability that 2 randomly selected 60-year-old females will survive the year? I'm going to say here, since we're drawing them randomly, yeah, so they're randomly selected 60-year-old females. They're probably not going to be related to each other and have the same health issues or anything. So they're going to be independent of each other, because if you select one 60-year-old female, whether she survives or not doesn't have any impact on whether the second one is going to survive. So these are going to be independent. So we can go ahead and use the multiplication rule for this one. So this one, it's worded a little bit funny. It says probability that probability that 2 randomly selected will survive the year. So this doesn't automatically look like a multiplication rule problem because it doesn't say the word and in there. this one. We're looking at the probability that they both survive. You'll have to notice that that's the same thing as saying probability that the first will survive and the second one survive. So we want both of them to survive in this case. We don't want or because we don't want one or the other. We want to make sure both of them do. So since we want both of them to survive, it's going to be an and problem. And because it's and, that and is going to turn into a multiplication, assuming that they're independent, which these ones are. So this is going to turn into the probability that the first one survives, and this one's the probability that the second one survives. And what's the probability that the first survives? Yeah, so that's that percent right there. But we're going to write it as 0.99186 because we don't want to deal with percents, we want to deal with decimals. So we're going to write that as a decimal, and then the second one, it's the same probability, it's still at 99.186%, so we're still going to have 0.99186, and we're going to multiply those two things together. That's where we get the 0.9838 if you round it. I just want to show you real quick. 9838. And that makes sense because it's a probability, so it should be in between 0 and 1. If you forget and you try to use percents instead on this type of problem, it's going to be, they're going to give you really funky answers. So you get 99.186. So if you just type that number out front of the percent right here, and don't change it to a decimal, and then multiply it by 99.186. What's going to happen is those decimals are going to be thrown off, and we still get the same numbers, 9838 right there, but it's going to be 9,838, which is way too big if we're talking about probabilities. They have to be in between 0 and 1. Maybe if you tried writing that as a percentage, 9,838% is still bigger than 100%. So technically you'll get the right numbers, but your decimal is going to be in the wrong place, just because that's what happens when you multiply with decimals. So that's why it's a good habit to get into with these ones. Always change it to a decimal first, never use percents, because otherwise you're going to get the right numbers, but your decimal is going to be wrong, and it's not going to make sense as a probability. Okay, so this one's a little tricky. All right, so we're looking at exercise equipment, and we know that 10% of their products are defective, and they say that only 30% of their customers actually use the equipment in the first year after it's purchased, which is crazy. But there's a 1-year warranty on the equipment. They say what proportion of customers will actually make a valid warranty. They say the defectiveness is independent of the use of the equipment, because if your equipment's defective, it doesn't matter if you're using it or not, it's just defective. That's why they say defective and not like you broke it or anything. So